everybody, I'm going to talk a little bit more about tautomerization in this video. So I do definitely think there was a little bit of confusion when we talked about it the other day in class. So I just wanted to kind of make this to hopefully clear some stuff up and take away some of the misconceptions that we had. So just to start with, we'll start with definitions here. So a tautomer is a constitutional isomer that rapidly interconverts via migration of a proton. So it's two constitutional isomers, so they have the same formula, but different atom connectivity, and they can rapidly interconvert via acid-base reactions, okay? That's what it is. So the tautomerization is that process of the interconversion. So going from one tautomer to the other tautomer, that process is tautomerization. So it's important to keep in mind this can happen in acid or base. Okay, so when we were talking about the alkyne reactions, we were talking about two different reactions that had either kind of acidic conditions or basic conditions. That had nothing to do with what the actual product was, because both of them were leading to an enol, and that enol was tautomerizing to its carbonyl tautomer. So the tautomerization can be acid or base. Nothing about the tautomerization was actually impacting what the product outcome was. Okay, that was all dictated by either the carbocation stability or steric interactions with the boron. All of that had nothing to do with the actual tautomerization. So acid or base, we can have this tautomerization happen. So this is an enol, okay? This is the tautomer of this ketone, okay? So when we're looking at this, we're looking at migration of a single proton here. So in this case, we're looking at the migration of this proton to here, okay? So we're really looking at essentially, in fact, two acid-base reactions, where first we're gonna have this leave and we have to have something add here, okay? So that is our tautomerization. So this can happen in aqueous, acid, or base, okay? And we talked in class about the preference of the ketone product. Alrighty, time to fill up my water bottle. So we have the keto and the enol form. So we talked about in class how this equilibrium was generally favoring the keto side. Okay, so this is the keto form, this is the enol form of these tautomers, which are in equilibrium with each other. So generally the keto form is favored because it is lower in energy. Okay, so there is a bit more of a dip down in the energy to stay in the keto form. So generally, most tautomers that are keto enol are going to spend more time in their carbonyl form than in their enol form. Later in the semester, we'll learn how to kind of force things into this enol form to be able to do reactions. But generally, the keto form is favored. The big difference here, or the kind of big exception, is this enol. Okay, we've seen this before. This is phenol, right? We've seen phenol, we've used phenol. This is technically an enol, but in this case, the equilibrium heavily favors the enol form and not the keto form. Okay, so in this case, the enol form is favored. Also because we're forming something that's lower in energy, because now we're forming a benzene ring, okay? So the enol is favored because the benzene is very, very stable. Okay, so we're still going, we're not really breaking any rules in terms of always trying to go towards the lowest energy thing. Tautomerization is all about that. It's just that in most cases, that keto form is going to be the more stable kind of well to sit in. And there's only kind of small little examples where we have exceptions to that, where the enol is actually going to be more stable. But whichever one is more stable, it's going to be the one that is the main. So in most of what we're going to do, we're going to stick to this kind of more generalized situation where the keto form is going to be our main tautomer that we see. So it is important to keep in mind that this tautomerization process and tautomers and everything don't belong to anything to do with alkyne reactions. It's really a lot more about the equilibrium of carbonyls, just in the fact that there's a lot of acid-base reactions that can occur to be switching between these two tautomer possibilities. So let's go ahead and talk a little bit more about the mechanisms of tautomerization. So I just want to kind of drive home that acid or base can both happen here. So we'll go ahead and start with some acid examples. Okay, so we're just going to use the same example that we had up above. Okay, so if I have this enol and I have this in an aqueous solution with some sulfuric acid, okay, I've got acid, I've got my enol. So if I have acid, the first thing I'm going to do is I'm going to protonate somewhere here. So when I'm doing that, we're going to go ahead and protonate that carbon. So we're going to protonate the alkene essentially. So now I have two H's over here and a positive charge left on that carbon. I do handily enough have that oxygen right nearby that I can use to stabilize that carbocation through resonance. And now that I have this form, now this H is much, much more acidic, okay? So it's important to keep in mind that when I just have an OH, it's not that acidic. So if I'm in acid, I'm certainly not going to start by deprotonating that. So I first need to get that H to be a much more acidic proton so that now I have something like water around that can actually do an acid-base reaction on that. Okay, so then I can get to here. So if I go ahead and do this exact same substrate with base, so let's say I have sodium hydroxide and water. So again, all the same stuff I need to be thinking about, except this time I'm in base. I'm still going to be getting to the same product. But now since I'm in base, I need to be thinking about my enol as more of an acid than a base now, okay? So I'm going to go for the most acidic proton, which in this case is the H on that oxygen. And we're going to start there. Okay, so I can go to this enolate, which is just the deprotonated form. I can again do some resonance structures here. That way we can kind of see a little bit better about how we're actually going about protonating here. I'm going to just draw that H in. Okay, and then now that we have that carbon much, much more basic, now we can go and deprotonate a water with it. And we get to the same product, okay? So the difference is here. I'm just gonna scooch this really quick. Okay, so in the acid, the first step that we did was we protonated the carbon. And then we deprotonate the oxygen. Okay, in the base, we do those things exactly flipped. So the first step we did here was we deprotonated the oxygen. And then we protonated the carbon. Okay, because if we're in acid, we should be protonating our substrate. If we're in base, we should be deprotonating. Okay, so other carbonyls can definitely do tautomerization reactions, which is kind of what we saw yesterday, which I think was part of what was leading to the confusion there. Okay, so if I have an enol that looks like this, okay, so let's just take a second to look at the differences here. The only difference is really that I have an H right here off of that alkene instead of having another carbon. Okay, so it's just that particular position that is changing the whole carbonyl type, but it has nothing to do with the actual tautomerization. I could even do a tautomerization with, let's say I had an OCH3 here. You can tautomerize that into an ester. Okay, so I'll show you that one in a second, but we'll stick with this guy for a second. So this one, again, we can do aqueous acid or base. And they're both going to get to the same exact carbonyl. In this case, we're going to be making an aldehyde because I have this H right here. Okay, so in that case, if I'm in acid, okay, so I should be protonating my carbon first. Okay, so I'm going to add I'm going to add one H, so then I've got two H's on that carbon, leaving me a carbocation next to my alcohol. I can stabilize that with resonance. And then I get to here. I can follow that up with a deprotonation of my oxygen now that it's much, much more acidic. And now I've gotten to an aldehyde. Okay, if I do that in base, we're going to see something very, very similar happen, except just like in the example above, we're going to see it happen opposite. Okay, so first step, we're going to see the sodium hydroxide deprotonate our OH. We're in base, so we're going to deprotonate first. Okay, I get to this O minus. It can draw a resonance structure just to kind of guide me where I need to be going here. Oops. Okay, so then I've got my negative charge on my carbon. I can go ahead and protonate that with water. and then I again get to my aldehyde. Okay, so if I was to do this for an ester, let's just say that I had OH, enol, OCH3. Okay, so this is also called an enol ether, because of course it is, because we love our names. So this one I'll just show with the acid, because again, hopefully you're getting the pattern of like the base will do the exact same thing, but we can just protonate the carbon, leaving a carbocation behind. We can resonance stabilize that new carbocation. And then we can deprotonate to get to our ester in this case. Okay, so whenever you're looking at an enol or something that looks like an enol, really think about the fact that all the carbon connectivity is going to stay exactly the same. Okay, the only atoms that are moving around are the H's. Okay, so when we're looking at an enol, you can really think about the fact that if you just start off by drawing a resonance structure, right? Because we can draw a resonance structure right off the bat to make it look closer to its carbonyl form. All you need to kind of think about is you need to remove this H and add an H over here. Okay, so if it helps to draw this resonance structure out before starting, just to kind of think about, okay, well, I know that this is where my carbonyl is going to be. I got to deal with this guy and I got to deal with this guy. Everything else is going to be exactly the same. Okay, so hopefully this clears some stuff up. As always, please let me know if you have any other questions, and I will see you all on Tuesday.